Okay, so starting with this lecture, we begin a new topic. So we're going to study Fourier series, so which is basically a way of representing apparently complicated functions in terms of certain kinds of special kinds of sums. So before we get there, we will recall some familiar concepts related to simple harmonic motion and very basic wave phenomena, right? So that's the subject of this lecture, right? So given our rather comprehensive understanding of linear algebra now, we will also try and bring in some of these concepts as we go along, right? In our discussion of Fourier series, it will turn out to be profitable to bring in some of these concepts of linear algebra, right? But all of that is coming a bit later. In this lecture, we are going to describe, it's mostly in the nature of recall. We're going to talk about simple harmonic motion and waves. Okay, so we are familiar with simple harmonic motion, right? So it's back and forth motion which is sinusoidal in nature, right? So I guess the most familiar object which performs simple harmonic motion is a pendulum, right? I mean within the small angle approximation, right? So you have oscillatory phenomena of all kinds, but it becomes simple harmonic motion if it is if we keep terms only to the lowest order, right? So in fact, so the solution is what I'm going to write down. So it appears in a wide variety of contexts, right? So harmonic phenomena are ubiquitous, and and it's often useful to start with the lowest order effect, which is simple harmonic motion, right? Where we consider that the potential energy, if you wish, has a purely quadratic term, or you can think of it as in terms of forces. It's going to involve a Hooke's law kind of forces involved, right? All very familiar stuff, right? And so the reason why simple harmonic motion is particularly important is because all functions with a local minimum, right? So the simplest kind of minimum will involve a quadratic type of function, right? And therefore simple harmonic motion it's very important to study because this is as simple as it gets. Of course, you can look at more complicated scenarios where higher order effects are present. Sometimes the lowest order is not even present and so on. But for our purposes, we'll start with the simple harmonic motion, and here we will directly look at the solution itself, right? I mean, the differential equation aspect of this will come later, right? So that's also part of our study, right? We're going to study differential equations, but for now, let's say we know intuitively or from our earlier studies that the solution for a simple harmonic motion is just y equal to a times sine omega t plus phi, right? So there is this phase factor, there is a natural frequency associated with this motion, and therefore there is a time period which one can equivalently define, and there is an amplitude of this motion, right? All of these are properties. So we'll just, since we are all familiar with this, we'll directly look at a couple of examples and identify these various quantities associated with simple harmonic. So given the distance of some particle, and if you know s as a function of time, let's say you're measuring s from the origin, and if it is given to be s is equal to 3 times cosine of 5t, right? So it doesn't matter whether it's cosine or sine, right? I mean, this is a comprehensive way of thinking about this because you have this phase, right? So this phase allows you to treat cosines or sines, it doesn't matter. I mean, there's a way to bring it back to this form. If you think of this as a standard form, of course, it's possible to look at this function 3 times cosine of 5t and bring it to this form. But we can directly read off from here. The amplitude here is going to be just 3, right? This is the amplitude. Then the frequency is, so it's the angular frequency, which is phi, and therefore the time period of this motion is 2 pi by omega, which is 2 pi by phi. You can also work out the velocity amplitude for this particle, right? You take the time derivative ds by dt, which will give you a minus 3 times phi you know, in general, it's going to give you, if you take a derivative of sine, it's going to bring out this omega, and this is going to become cosine, right? And so the phase is going to be, you know, there is going to be a shift in the phase, but it doesn't matter so much because we're looking at, if you're interested in the amplitude. So that's velocity amplitude, and that's going to be just a times omega, which in this case is 15, right? So the amplitude is always taken to be a positive number. It's the magnitude. And sometimes, you know, blindly looking at the functional form, you know, one may be deceived into concluding that it may not be SHM, but if you're, you know, carefully, you know, arrange the terms in a suitable way. So like in this example, right, using trigonometric identities, we can recast this functional form in the following manner, and in fact we'll be able to check that this is 6 by root 2 times sine of 2t, right? So it looks like there are two terms, but in fact actually this is just, you can pull out the 3 and then add these, right? So you use the identity sine of c plus d plus sine of c minus d and carefully collect terms. You will get only a simple harmonic motion whose amplitude is 3 times root 2 and whose velocity amplitude you can compute to be 6 times root 2 and whose frequency is omega equal to 2, time period is pi, right? So this is all familiar stuff, which is you know, from high school we have been looking at these kinds of phenomena. Okay, so we are also familiar with a moving wave, right? In 1D, if you take a snapshot of a wave at some time, it may look something like this. It's a sinusoidal curve, right? So a wave, to represent a wave, you need to provide information, an infinite amount of information in some sense. So you need, it's a whole function, right, at a given snapshot if you're taking it. And then if you you know, wait for some time and ask what is the, take another snapshot after some time t, it's going to look, you know, sinusoidal again, but the whole sinusoidal curve would have moved, right? So if there is some speed that you can associate with this wave, so then we can ask, we can you know, argue that the value of y at the point x is just the same as the value of y at the point x minus vt, because the whole wave has moved. So you know, using this argument, you can actually write down the functional form for this wave, you know, in terms of x and time. So there is, so in this case, you know, not just there is a wavelength associated with it, so it's a pure sinusoidal wave that I'm thinking of here, right? So there is a wavelength associated with the wave, which is information that you can get by looking at the wave at any snapshot, at any time instant. And then there is also, you know, a dynamical component to this, the wave. The wave itself is moving as a function of time, so that brings in another parameter, which is the speed of the wave. So, you know, we can think of, you know, this entire function, it represents a moving wave, right? So another way of thinking about you know, a moving wave is, you know, to think of, to look at what a particular point is doing. If you fix x and look at what that particular point is doing as a function of time, you'll see that it's really, you know, the same as this equation that we had earlier. That's simple harmonic motion. So you basically, what is happening is that you have, you know, infinitely many different particles, if you wish, or positions x. Each of them is performing this simple harmonic motion, right? And you know, there is this very precise phase relationship, and therefore all of them conspire together to create this wave. So you can either think of this as, you know, every point performing a simple harmonic motion in a very you know, precise manner, or you can, as you might see if you plot this as a function of x and t, it's the whole wave which is propagating as a function of time, right? So there is a, you know, many different ways in which the same wave function can be written as, right? So and you know, each of these forms is instructive in the sense that it, you know, it carries information about a different quantity involved, right? But they're all connected together, as you are familiar, right? So you can check that indeed all of these forms are completely equivalent. So there are, you know, inbuilt in this are notions of, amplitude. Amplitude is of course the same in all of these explicitly, and then there is a wavelength which is used here. Sometimes the wavelength appears in this form in place of the speed. It's more convenient to put in this kind of a time period, and or there is an omega that you can work with, or you can work with a wave vector and so on, right? Period, speed, the standard relationship between these quantities, and I'm just collecting together information that we all already have, right? So this is like a warm-up lecture to Fourier series, right? So we'll describe in a step-by-step manner the context for coming up with a Fourier series, and then we will see how to get a Fourier series for a periodic function and so on, right? That's all for this lecture. Thank you.